This video is for section 14-2, the remainder theorem and the factor theorem. By dividing this trinomial, this four-term polynomial, and this polynomial, each by x minus 2, we obtain the different quotients shown in this chart. So in the first column of the chart, we have those four polynomials. When you divide by x minus 2 using long division, something we studied in a previous section, it creates this quotient with this remainder. Again, think back to the long division section when dividing polynomials by other polynomials, getting the answer up above the long division bracket, and then writing the remainder in a fraction form. The last column of this chart shows the value of the polynomial when x equals 2. That is, if you take each of these polynomials and substitute 2 in place of x and work out the answer, it makes the number shown in the last column. So like on this first one, when you input 2, the answer turns out to be -4. On this second one, when you input a 2 and work it out, the answer turns out to be 0, and so on for the 4 rows. What do you notice about the remainder, which is shown in this column, and the value of p of 2 shown in the last column? Well, hopefully you notice that the remainder is the same thing as p of 2. So we could write they're equal, or they're the same. This suggests a theorem called the remainder theorem. For every polynomial p and for every number r, there will exist a polynomial q with degree 1 less than the original polynomial, such that the polynomial factors into this format. What this is telling us is that when you divide a polynomial by a binomial that's linear, the answer will have this look to it. Let's try an example of this and see that. The example is use synthetic division to divide this polynomial by x minus 3. Write down the coefficients from the polynomial: 6, -19, 1, and 6. Make the synthetic division bracket. Then we're going to divide by a number that is written out front. Based upon the symbols used in the remainder theorem, we can see that whatever this number here is after the subtraction sign, that's what we're writing out in front. So in our problem, if we want to divide by x minus 3, we can do that by putting a 3 in with synthetic substitution. Now let's run through the process. Pull down the 6, then multiply, making 18. Now add these, making -1. Now multiply, -3. Add these, which is -2. Now multiply, which is -6. And add these, and the result is 0, meaning there's a remainder of 0. X minus 3 divides evenly into the polynomial. Let's write our answer down. To do that, we need to translate this list of coefficients back into polynomial notation. This last number is the remainder. This number here is the constant term. This number here will be the coefficient of x. And this number here will end up being the coefficient of x squared. So here comes our answer. 6x squared minus 1x minus 2. And then if the remainder is 0, you don't have to put anything down on the end. We have divided the original polynomial by x minus 3, and we did not do it with long division. Instead, we used synthetic division, or the other day we called that synthetic substitution. The remainder theorem leads to the factor theorem, which we actually already saw in section 4-10. The factor theorem is, over the set of complex numbers, this binomial that's linear will be a factor of a polynomial if the remainder is 0. Let's use that idea to solve this next example. Is x minus 4 a factor of this polynomial? We want to know, does x minus 4 divide evenly into the polynomial with no remainder? That's what it means to be a factor. Let's not use long division, because if you remember from a different chapter, long division is pretty complicated. It's easy to mess up as you are subtracting the different columns. Instead, let's use synthetic division. So write out the coefficients. 1, -3, -1, -11, -4. Then make the synthetic division bracket. Now what number are we going to divide in? It's this number here that comes after the minus sign. Another way to think of it is you're going to divide in whatever value of x makes this binomial equal to 0. So like, what minus 4 makes 0? That would be a 4. Now let's run through the process. Pull down the 1, then multiply, add, multiply, add, multiply, add, multiply, and add. The remainder is 0, so are we going to answer yes or no? Is this a factor when the remainder is 0? Yes, it is. Next example. Use synthetic division to factor the polynomial. So first, write down the coefficients. 1x cubed, 2x squared, -2x, and 3 is the constant. Make the bracket. R equals 2 is our hint, so we're going to substitute in a 2. Pull down the 1, then multiply, add, multiply, add, multiply, and add. Now we need to translate these results into this form that we're asked for. So first it says x minus r. So in parentheses we have x minus 2. Because remember, we were told r is 2. Now there's a times and q of x. So q of x is the polynomial that we get when we did the division. Now this plus p over r, that's the remainder. And the remainder is this very last number. So here's our remainder, or the value of p of 2. These three coefficients can be used to find this q of x polynomial. So we got to think about what they represent though. As you're moving to the left, this one here is the constant. This one here goes with x. This one here goes with x squared. So it's 1x squared plus 4x plus 6. Notice that there's now a plus sign, and then the remainder, 15. This answer that we've created fits this format that we were asked to use. Let's summarize the lesson. This was all about using the synthetic substitution technique, or you can even call it synthetic division. It means the same thing. It was about using that technique to do a couple different things. One, it allows us to figure out the value of a function. Two, it allows us to decide if a binomial is a factor of a polynomial. And three, it allows us to factor a polynomial by rewriting it as a product of a binomial times another polynomial.